So before we start, we just want to talk about some admin thing first. First is we're going to schedule the test time on the last day of the semester. So I would, because it's a 1 hour test, so we just make it like 4:30 to 5:30, 6:30, 6:30, 7:30. So I want you to tell me which is the most convenient so that we could try to make it possible to make sure that to minimize the inconvenience that we're getting. So just this is coming from the announcement on the Zoom. You just go to the announcement. There will be link to the Google form. So please try to fill that in. And the second thing I want to know also on the Friday, I want to let you know the deadline for the homework 1. So I noticed many of you have submitted already. So just make sure that you don't miss the deadline for that. Because the system only allows single submission. In case you want to resubmit, you just have to email the TA for that. Okay, but okay, if there's no question, let us talk about random variable. Today, I guess things are not that hard, but we have a bunch of assumption or definition to understand, because we don't go to those details, so you will be a display of facts, and I try to explain and I should demonstrate by examples. So little bit some learning, but will not be very hard. But so let's get started. Random variable, let's review what is this. Okay, what it is basically just like you just put numbers to the outcomes. Okay, remember the random experiment, we have outcomes, right? Or and then the outcomes can be rather complicated to describe, and in those cases we're interested in numbers that relate to outcomes, and usually we want the assignment of the numbers to be meaningful, right? And say, for example, we have this example 1 is total and coin. Once we have a head and tail, and it's not clear what number you're trying to assign. Okay, you can probably say head is 1,000 and then tail is 10. I mean, any number you can assign to head and tail is not, it's okay, it's a random variable. Hey, you want to make the random variable to be a meaningful one, right? So one way to do it is has to be something like number of heads or number of tails. Okay, the same because it only tells once, right? So here we have head related to 1 and tail related to 0. Okay, so that's how later you see actually we use this formulation as well. And here we have the coin tossing is twice, right? We have head, tail, tail, head, and tail, tail. And of course, as you can say, head is 4, head tail is 3, tail head is 2, and tail tail is 1. You can do that, right? You can put any number you want without any problem. Okay, could be random variable. And then we actually want the number to be meaningful, as we will see very soon. We want to calculate the expected number of head, variance of head. You want that number, the random variable, to have some meaningful idea. And here we say number of heads. Okay, you can do number of tail, there will be no difference. As long as a fair coin, will be symmetric. If unfair is also fine. I mean, but there will be a little bit different. But here we assign tail tail to be 0, head tail tail 1, and head head is 0 to 2. So in this particular formulation of random variable, you can see that we ignore the order, right? Because number of basically just count head, tail, or tail, head same. Okay. So this random variable actually serves two purposes, right? One is you put a number to each outcome. And second, you simplify the sample space. Basically, this strings reduce complexity. Okay. So that is the two benefit of using random variable. One is become number. And second is it makes things more easier, right? And you when you change the number, okay, everything we learned in topic 1, summary statistics will be meaningful, right? You can calculate later. Actually, we see we can calculate mean and variance. Actually, you can also calculate kurtosis or skewness, but we don't talk about that. But that would be something we'll work on, okay, very soon. So we also distinguish two things. We distinguish random variable by support, right? What is support? Support is the value that you can assign to the random variable, okay? And they can be either discrete or continuous, okay? And the reason why we have to separate the two because of the mathematical tools that we have to use. And discrete, you can use the classical method that we have been learning in the high school. There's no problem. Just addition, subtraction, or division, everything would work nicely. But for continuous random variable, okay, you cannot use the usual one because discrete means that you can basically count them, or there's countable infinite. You can basically do things easily, but the continuous, the standard way of addition, subtraction would not be enough. So we require what we call calculus, right? You need integration or differentiation, okay? I mean, don't worry, we don't talk about those things in our class, but we need a little bit different way to handle those things. So that's why historically we have to, or mathematically or practically, have to divide them into two parts. But don't worry, you will make clear what they are, and to you, when you learn it as a first course, they look very similar for our purpose. Of course, mathematically very different, because we know from mathematics what is finite and what's infinite is a very different thing. But anyway, so you can basically think about discrete is something like 1, 2, 3, 4, 5. Okay, that is something, number of consumers, number of problems, number of accidents. These things are discrete. Okay, and we talk about continuous random variable is like something is easy to think about. If one value is an outcome and the other value is outcome, is the intermediate value is outcome? If that's the case, then is continuous, like temperature, stock market, price index, right? Anything in finance, anything with price is continuous random variable. So it should not be a problem to see how they're different, but later you will see there's some reason why you want to do it. Okay. In many cases, continuous random variable is something usually what you're actually measuring, right? The temperature, right, and also the stock market index is something actually we usually calculate that. Okay. So and we first talk about discrete random variable. I think we're able to finish that, but the continuous we have to wait for the next class, Tuesday, also Thursday. So hopefully we're able to finish this whole thing because it's not very complicated. Okay. So the good thing about discrete random variable is you can easily describe them, right? Because it's they have a countable number of outcomes, right? And then each outcome would have some probability there. And for each value, you tell them what is the probability. That is called the probability function. Okay. Basically, just tell you that at this value, small x, what will be the probability? Okay, that is very simple. There's nothing very deep here. The only thing that is a little bit slightly more challenging in terms of concept is we have what we call the cumulative probability function. Okay, that is basically the p, but adding everything before the value of x. Okay, as you would probably ask why we care about this. It's not immediately clear why we care about this when we talk about discrete, because discrete is completely, you can do this one. And why you care about this is later you will see when we talk about continuous random variable. This is the big F is the thing we care. Okay, because we don't have the P thing in the continuous one. I mean, there will be something related, but it's not easy to understand. But this one is a thing we would do. So then that's why we introduce here. Okay, of course, there are other reasons why this is used, but you can see the two representation. Okay, is different way to look at the object. Okay, you can convert one to the other. Okay, so let's see the example, then try to convince you that's the case. Okay, the simplest you can imagine is putting a coin, right? And we use the standard idea number of head or number of tail as you want. I mean, because it's fair coin. So x is 0 or 1, right? And p of x must be 1/2 because it's fair coin, right? And the only difficulties lies on the fact that that is how you do the big F of x. Okay, the p of x is something very simple. Just this is just saying this is the tail, right? This is head, right? This is just simply look at construct from the p. Okay, look at the p. Okay, what is this value? And all the value before it will be this f. Okay, so we only have 0, so there's nothing in front of it, so it's just same as this one. Okay, and look at this, why this is 1. Okay, this is 1 because you just pick up all the thing above, okay, and before it. Okay, so 1/2 plus 1/2 is 1. Okay, so that's how you construct the f. Okay, so there's nothing deep here, but rather just a new way to represent. And then you can easily see that you can do the similar operation to get the p, right? So if I give you f, you can also do the p as well, right? Because the first p, okay, is same as the first f, okay? And the second p comes from what? Second p comes from the difference between the two f. You take a difference, you get the p immediately above. Okay, so it doesn't really matter you do it by looking at the p or looking at the f. Okay, the same thing. Okay, just like how you look at things. Okay, so I think last time I draw a graph, right? So you can easily see. Let's see, can I reproduce here? So you can see if I have x, I have a p of x, all right? And this is 0, this is 1. Okay, I use the red one here and the blue one here, right? And they're all 1/2, right? And I can also draw the same x here, 1/2 is here. Okay, I have f of x, right? I also have 0, 1, okay? And how you construct this is this red one, same as this guy 0, okay? And how you do the next one is you have the blue one here, right? And then you stack everything before it, right? Just red here, okay? So that's how this is 1, right? So this is how you enable yourself to get the complete to f, right? You can also go from f to p. You just look at this, right, and subtract everything. Subtract the top part, right? The extra part will be, take out the extra part will be the blue one, right? So that's, you should able to see how you come from p to f or f to p. Is that clear how you get from that one? Is there any question between P and F? Okay, I hope that's okay. And let us see a little bit more interesting problem. Okay, is you throw a coin twice. Okay, and we have a number of heads, right? So basically, the random variable say the following, right? So this is mapped to 2, and this 2 guy, right, goes to 1, and this guy goes to 0. Okay, and because it is a fair coin, okay, the 4 outcome is equally likely. So each outcome has probability of 1/4. Okay, so that's why first one you see the 0 is means TT, right? So that's why I say a quarter here, and 1 is represented by HT and TH. Okay, so it has 2 outcome here, right? So that's why it's a 1/2. And the last one is HH, right? So that's why it's 1/4, because only 1 outcome out of 4 possible outcomes. Is that clear how you construct the P? Okay, and how you come from P to F, right? It's very simple, right? So this is just looking at any number above and behind it, only 1/4. And 3/4 is coming from the number above and behind it, right? So it says 1/4 plus 1/2 is 3/4. Okay, and the last one comes from above and behind, right? It's 1/4 plus 1/2 plus 1/4. That's 1. Okay, that's how you can construct that. Okay, I think it's okay. I don't need to draw a picture for that. I think it's very clear. If I give you F, you can do P. I give you P, you can do F. That's the different way to look at the different thing. Okay, and I just to remind you that why we want to do that is because when we talk about continuous random variable, the pick F is much more convenient to think than the P, because it's not easy to think about continuous. What's the P there? Okay, but later you will see. I mean, just don't worry. But just we learn it now, but we will see more clearly when we talk about that later. Is that okay? Okay. Now let's see this another example. I think I will go very fast for this one because it's trivial right now. So this has rolling a die that with 6 outcomes, right? So naturally you want your random variable to be exactly what the face value is, right? Just from 1 to 6, okay? And each outcome is equally likely. So that's why the P is just, everything is just 1/6 for every outcome, because this is a fair die. Okay? And just to remind you how can you use the F, right? Just look at above and smaller. Okay, just go in this direction, add up everything, right? And same for 2, right? Just pick this number, comes from everything above and before it, right? I'm not going to do for every single entry, but that's how you can calculate. Okay? And just to remind you how you get from, finally, how to get the P from F, right? So you subtract this guy and the guy immediate before, we'll get the P of this one, right? You subtract 4/6 minus 3/6 is get 1/6. Okay, that's how you get these numbers. Okay, I don't think I need to talk more about that. Okay, and this is usually how you would draw it. You use a bar chart as the way you want to show it, say for business purpose, right? And if you look at statistics textbook in the math, they would do in this way. The reason they want to do in this way because mathematically, these are all zero value, okay? Only at that particular point, you have some number. Sorry, this is P, there's a typo here, there's a P. Okay, there's a P here. So that is exactly what you would see when you try to pick up a more advanced textbook as the statistics textbook. Okay, they don't use bar chart, but they actually plot out the whole function, and they would just show the zero there. But for business application, I don't think if you show this is too nerdy, right? I mean, that's why I put it technical. Let you know if you see the book like this, that is actually the right way. But when we present it to your boss, to your customer, I don't think they'll appreciate this very strict format, right? You would rather show it in this way. I think people understand easily than this one, okay? So, but technically, this one is the correct one. This one is rather incorrect because it didn't show it is zero, right? Actually, it's not just only 1 point there, but I don't think anyone would confuse for that. So that would be the way you do it. And you have the F, right? You just like 1, 6, 2, 6, 3, 6, 4, 6, 5, 6 to 1, right? Again, this is a little bit, this is right, but this is not correct because the actual one is like a step function, right? Because between 1 and 2 is still the same as the 1, okay? So this f of 1.5 is same as f of 1. So that is actually a step function. I mean, you really, if you really care about the formality there, okay? And for those who are doing the quantitative finance, then this is the one you should be thinking about. I mean, but when you really present to your client or your boss, this would be understood, right, in this way. It's not, there's no problem in this way. But remember, in the reality, this is what the math defined, because the definition said the probability that x less than or equal to x, right? So x less than 1 and less than 1.5, the same thing, okay? So that's why it is not 0 here, okay? There will be something, okay? So, but do note that, I mean, this is okay, perfectly fine when you talk about a business presentation. Just let you know, this is not the exact form that should be there, but just to remind you, okay? I will be keeping the business format in the rest of presentation, but just let you know, this should be the right way, okay? Unless there's some special thing I need to show the formal one, but otherwise I will keep this one, okay? Is there any question between for this too? Any question? I hope after the weekend, I hope this still you can still remember. Okay. Now, as we said, now we basically have some numbers representing some outcome, right? It's very natural, very tempting, right, to consider the case we learned from our first class, right? Can we do some summary statistics on this random variable? Okay. And what does that mean? Do they have meaning? Okay. The first immediate thing you can think about is mean, right? Or average. Of course, the median or mode or everything actually is well defined, that there's a meaning there. But for our class, we focus on basically two things, mean and variance. Okay. You may ask, is it kurtosis and skewness do have meaning? Yes, they do. But for our purpose, we just focus on mean and variance. Okay. And mean and variance, especially mean in this context, we don't talk about mean. We'll call it expectation. Okay. And the idea is somewhat simple to see. The define is the weighted average. Okay. And we'll use probability and weights. Okay. And the definition is expected value is called E of X is summation X times P of X. Okay. So probably you want to see what is this there. Okay. So you can actually imagine, look at the question, look at the example again. Let's see why this would make sense. Okay. First, we can imagine that like a random experiment, suppose we repeat this many times. Okay. And the P of X actually will become the relative frequency. Right? Suppose put it this way, okay? Make you easier to think. Consider the following, okay? This example will be easiest to think. Okay, let's look at the loading a fair die, okay? And each outcome has likelihood of 1/6, right? And that 1/6 will be 1, 1/6 will be 2, 1/6 of 3, 1/6 of 4, 1/6 of 5, 1/6 of 6, right? And if you repeat this, say 6 million times, okay, 6 million times, fair con, and many times, as we are saying, how we derive probability, right? Is we define as we keep this experiment many times, it's a ratio, right? And you expect 1 million, you get 1 million times, you get 1 million times, you get 2, 1 million, 3, right? So if you actually calculate the mean value of the die, right, will be 1 million times 1, right? Plus 1 million times 2, plus 2 million times 3, blah, blah, over 6 million, right? So that means repeat this is you repeat 6 million, right? You calculate what is the mean of the data, right? So you run this experiment, maybe you get 1, 1, 2, maybe 6, 4, 3, blah, 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 you repeat 6 million, right? So what the data you will get is you will probably have 1 million for each, right? So basically what you get is 1 million, maybe I just have a 1 million, right? Times 1, right? Because 1 million, 1 plus together, right? And you have 2 million, again, 1 million times 2, so on and so forth, right? And plus 1 million times 6, right? Because each would appear 1 million times, right? And you would be dividing by mean, right? There, how many rows were done? You're doing 6 million, right? And do note that this ratio is what? This ratio is exactly probability, right? Is the denominator, right? Is total number of experiment you done, right? And the numerator is the number of outcome favorable to the event, right? So basically what you're actually doing will be the number you get times the probability, right? So it's exactly the weighted sum idea, right? So each outcome times probability, okay? And what you get, this one is expected value, which is 3.5, which we will work again later by that. But this is the number, is what you get is actually repeat this experiment many times. You get a data there. The mean is 3.5. Will be same as what we call expected value. Is that clear what we're doing? Okay, it's exactly opposite the case when we define probability, right? Probability will be defined as we actually repeat the experiment many times. The probability we get is the ratio. Okay, now we do it reversely in our mind. Okay, in our mind we reverse the process. Okay, we tell you that the probability of the experiment is this and this. Okay, and you repeat this in your virtual mind. Okay, and you would expect 1/6 of the time you get 1, 1/6 of the time you will get 2, and so on and so forth, right? And you repeat this experiment. Actually, you calculate the mean being from the data, okay, will be given by this expected value. Is that clear what we are doing? Is it clear? Is that okay? I mean, it's a little bit, I mean, of course, if you forget, it doesn't really matter because we will just be using this definition, but I want to convince you that this is actually, although it's called weighted mean, but it's exactly the mean idea, okay? Okay, although we call it a weighted mean, but it's exactly, as I said here, you repeat the experiment many times, okay? And the relative frequency, okay, is actually the what you want to do, okay? You want to calculate in this way, okay? And usually as a method notation, we call this mu of x. Okay, this is usually you write it. Okay, so and in the other word, if you try to, I don't put it here, but if you say, if I just repeat this experiment many times, on average, this is the value we get. So this is expectation. Later we will show, we argue, probably we don't have time to show. We argue that if we are trying to guess what is the value coming from the random variable, this mean is the variable that we can guess. Okay, suppose you roll a die, fair die. What is the number? Okay, there's the best, right? That would be the mean would be the best, right? So remember what's the mean here? Remember number line here, right? X, we have 1, 2, 3, 4, 5, 6, right? There will be 6 data point here. Okay, and what we say the mean will be somewhere in the middle. Okay, this guy, actually looking at the distance, okay, between the outcomes, right? And 3.5 is in the middle. Okay, of course, the difference between this and here is we actually have many data here, right? Because we repeat many experiments, right? This you can actually have many data point here, right? There are many 2, many 3, many 4, many 5, many 6, right? And if you repeat 6 million, the 1 million of 1, 1 million of 2, 1 million of 3, and so on and so forth, and you calculate the mean exactly in the middle. Okay, so I hope I convince you this expectation is a relevant measure for what we want. Okay. And just a simple example is you roll a coin once, okay? Number of head, right? And just to remind you the table, right? X have 2 values, 0 or 1, right? P of X is 1/2, 1/2, okay? So this how you get it is 0 times 1/2 plus 1 times 1/2. Okay? So that's how you, because the definition, right? Expectation is just adding up all possible value of X times the value of X here, right? So we start from X equals 0, 0 times P of 0, plus 1 times P of 1. Okay? So I hope that is clear. And similarly, you can calculate expected value of rolling a die, right? And just to remind you why this is the case, right? X can be 1, 2, 3, 4, 5, and 6. And P of X is always 1/6 because it's a fair die. Okay. So we just 1/6, 1 times 1/6 plus 2 times 1/6, 3 times 1/6, 4 times 1/6, 5 times 1/6 plus 6 times 1/6 gives you 3.5. Actually, we calculate that. Okay. Is that okay? So this is something we expect in the mean if you repeat this a lot of time. Okay. Is that okay? If that's okay, then we will talk about a little bit more about what we call the linear property of expectation. Okay. Although it looks complicated, okay, this name, but it doesn't mean difficult. The thing is, like, if you care about the multiplication of the random variable, you can just take it out. Okay. And if the random variable adds some number, you just add out. Okay. And you combine these two would imply if you have a linear transformation, you multiply something plus some constant, you can just calculate the expectation first before you do this. Okay. Similarly, this is something. If they're adding two things, okay, you can take out the A and do it. Looks like something you can treat it as a thing by its own. Okay. And why this is important, right? Probably you may know this already. You can imagine that if this does not hold, then our life will be very difficult. Why? Because say for example, X is the price of certain stock. Okay. Maybe, I don't know, Hang Seng Index or maybe HSBC or Alibaba, whatever. And if, say for example, the first one, if expected A of X is not A times expected X, then our life will be miserable, because we have to think about what is the random expectation for price of one stock, price of two stock, price of three stock, price of four stock, five stock, so on and so forth, right? But with the first line, you don't need to worry about that. You can only care about only one single stock, price movement, one stock, and then that's it. You don't need to worry about those, right? And if you buy 1 million of the stocks or 1,000 of stock, the calculation is say, just take it out, we just multiply. Okay, the same idea here. You're like constant doesn't really matter. Again, in terms of investment, right? The B may be you how many cash is in your bank, right? X may be stock, B may be bonds or cash in the bank, right? So in terms of if you try to evaluate this portfolio, you don't need to worry about this. Okay, you can separate the portfolio calculation of the stock and the cash, right? Because cash is not moving anyway, put in the bank, so we can separate this calculation. Okay, so these things are not very trivial. Later, I mean, if you ever do finance calculation or accounting calculation, they can become much easier, right? So if you, in terms of terminology, this makes problem scalable, right? It's like you can solve the small problem and then just focus on something very simple and then add up, right? So you don't need to worry about too many things at once, right? So that's why you can do portfolio analysis, right? You can study stock one by one, right? If there's no interaction between them, of course, when the interaction between them, things become different. But as long as there's no interaction between them, things become easy. And at least for expectation, we don't really worry about interaction, okay? In terms of mean, right? If X is a stock X, Y is stock Y, in terms of calculating expected return, you don't need to worry about the interaction. Just looking at the mean of X and mean of Y separately, okay? So when I talk about the return of expected return of many projects, I don't need to worry about whether two projects is going to complementary or substitutable, right? Or mutual beneficial to each other. Where about synergy, don't need to think about those. We just do it separately. If we care about is the expectation. Okay, so that is the thing. And later, actually, we see when we talk about variance, this doesn't hold. Okay, although we don't cover multivariate thing, but you should see covariance is important idea here. But we will not go to that. But especially for those who are doing the quantitative finance, you have to care about those. Okay, but for the moment, we forget about that. Okay, so this is something that, I mean, later when you work on this kind of problem, you will actually be very comfortable using those. Okay, but you will not notice actually we have this assumption. Okay, and you probably ask why this thing would, why all these are correct. These things are correct because our expectation are simply the weighted sum, and adding things together, addition, actually all the things satisfy the property of addition, but I don't think you would want me to prove it. So we just skip everything there. I'm not going to prove anything there. Okay. So here comes the second part. Is that okay for the mean? Okay. I think I want to talk about the variance. Okay. But you can see this variance actually the same meaning as what we learned. Okay. It just look at each value minus the mean, take the square, okay, times probability. Okay. Look that this is no different from what I said at the beginning. this is exactly the same variance. If you do the experiment, okay, you repeat the experiment many times, okay, and px will be the relative frequency, right? I mean, how many times, what the relative percent in terms of percentage appears for x, right? And this is the mean, right? Just subtract it and take a square times this is exactly the variance, right? Because remember, what is variance from your first, maybe just take it in case you forget, okay, is what we call the average square distance from mean. Maybe just take it out in case you forget. Let's take out the first slide. Okay, how we define variance. Okay, variance, okay, as we define, is average square difference from mean, right? So that's why is this average distance from mean, okay, is average, right? Expectation of the square difference from mean. Okay, so the difference between this is, in the topic 1 we use the average, okay, but now we use expected, okay, or expectation of the square difference from mean, the same thing. Okay, so just to remind again, it's just like you repeat this experiment many times, okay, and then you record the outcome as dictated by the random variable, right? You just look at the outcome, you change the number, okay, and record those numbers down there, and calculate the mean, right, as usual, and you can calculate variance as usual, okay, and this variance is actually what you get. Okay, again, you may ask what's the meaning why we care about this, right? It's exactly the same idea why we care about variance, right? It's looking at how good is our expectation representing the random variable, right? If the variance is small, right, the expected value is good enough, right? It's very good, right? When the variance is big, our variance is not so good, right? And you can, as I said, beginning, you can easily think about kurtosis and skewness in this framework, but it's out of the scope for our class, okay? And they are important, but it's not very important, okay, for our class, okay? And as I mentioned in the first class, those things are super important when you're actually doing real application, put the real money in, and ignoring those that have catastrophic effect. Look at the historical development, okay? But for our class, we just happy with mean and variance, okay? And just to show you an example how you calculate variance, right? Remember it was 3.5. 3.5 is the mean of the row we die. 1 up to 6, right? This is the mu x, right? This is expected x. Okay. Okay. And remember this x, we have 0, 1, 2. Oh, there's no 0. It's 1, 2, 3, 4, 5, 6. And each one, okay, p of x is 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, right? And we know the expected value of x, right, is actually 3.5. Right? So that's why every number you take the x minus the expected value of x and take the square times 1/6. Is that clear how we do it? And this is exactly same as what you learn. You calculate this when you do in the variance, right? Is that okay? Is that clear what we're doing? Okay, just nothing, but you just reverse what we do in the probability, right? We tell you the probability. You just imaginary thing. We repeat this a lot of time, and you get the data. You get the mean and variance. Okay, is that clear what we're doing? Okay. Now, before we break, I want to talk about this quickly. Okay. Variance. Okay. For our class purpose, we are not going to prove any of this. Okay. But just let you know these are the formula, and you have to be very careful how they can be applied. And that is a little bit trickier. Okay. On top of the tricky thing, is okay. So the variance is this is definition. Okay. And this definition is very hard to do calculation usually. So if you ever try to do calculation, this is much easier. Okay. And why is the case? Because the following reason. Okay. X, you have 1, 2, 3, 4, 5, and 6, right? So x squared will be just 1, 4, 9, 16, 25, 36, right? So that means that expected x squared, right, will be just 1 times 1, 6, right? 4 times 1, 6, 9 times 1, 6, and so on and so forth until 36 times 1, 6, right? That you can give this number, right? You get everything up, you get this number, right? And this number, you already know is 3.5, right? So by using this shortcut, that make your life easier. So can you see why this is faster, right? Of course, this is only useful when you don't have calculator, right? Or you don't have computer fast, right? And in terms of Excel, everything become very easy. But this is much convenient. And in terms of proof, this is also easy. Okay. But I think for your purpose business application, I don't think that would be important. But it's important when you try to read the proof. I put in the book or put in the slide that I will take it as given. And this can be proved easily. And I put in a slide, but I'm not expecting you to reproduce. Okay. So this is just for the formula that for easy calculation. Okay. The next one is the very important formula here. And of course, if you learn math in the high school, that would probably you know already. Okay. So this formula is something rather have a deep interpretation. Okay. First, look at the variance. Okay. And you can see I have a constant b at the end here, plus b. Okay. And b appear nowhere in the formula. Okay. The reason is being that variance is measuring how data spread, right, compared to the mean, right? And if every data point is moved to the right at the same magnitude, right? Therefore, right, where b can point negative, right? So it shouldn't affect the variance, right? Because they all move in the same direction, right? So that's why it would be nothing in this variance. Okay. And the second thing you will see is the following: is we have multiplied by a. Okay. The variance will be multiplied by a squared. Okay. So if you say double your magnitude, right, the variance actually will be quadruple. Okay. Because if 2a then become a is 2, then a squared is 4. Right? So the variance will be much larger. Of course, immediately you will see, that's why usually we talk about SD, right? SD, we don't have this problem, right? When we talk about standard deviation, you don't have this problem, right? But for the variance is, you have to take square, okay? So this is something rather important, okay, in this context. Okay. Lastly, I want to talk about this formula here. Is okay, it's very important condition is if they're independent, okay, if they're independent, the variance of two parts is just you can take it separately. Okay. So the variance of stock Y and stock X is just the sum of the variance. Okay. It's just like the variance of X like this, the variance Y like this. They combine together, the variance is just adding up. Very simple. If they're independent. Okay. Now, Before I break, I want to show you one technical point. Before I'll talk about this after the break, but in case you want to know what happens if they're not independent, okay, you have to rely on certain what we call covariance term there, okay, and that explains somehow why I talk about in the very first topic when we try to select stocks, okay, we want to have stock that have negative covariance because the total variance drop, right? Because variance meaning the riskiness of portfolio. So that's why you want to choose, if you want to have two things in your portfolio, you want them, okay, to actually have negative covariance or small covariance, okay? Actually, there's a standard idea is you don't want to put all the eggs in the same basket, right? You want to separate reduce your risk. One way is to invest less risky asset, but if that is not possible, then you try to combine assets that is not moving in the same direction, right? So that's why, I mean, in investment, right, you try to put, say, what we call defensive stock, right? And what is that is the reason because defensive stock tend not to covariate with the whole market. But let me stop here. We will resume talking about the example. Okay. So go around to see if you have any question. Have a break of 10 minutes, I guess. Just one very technical thing is someone let me know the announcement is 2nd of December, but in the form I have 3rd of September, but it's the 2nd of December, so it's Friday, last day. So just 1 hour test, okay. So some of you asked me the past test. I release later stage, but to let you know what you might be expecting. But if you know how to do homework, then most of the questions should be very similar or straightforward. Maybe of course there's some variation, but you will see. Okay. So this is the example that how you calculate variance. Okay. So we have a outcome of head and tail, right? And x so it's twice. So the sample space is not this guy. So I have a mistake here. The sample space must be HH, HT, TH, and TT. Sorry, there's typo here but you know it from twice. It must be this one. Okay. So number of head, right? So we have basically again this is 2, right? And this 2 are 1, and this is 0, right? So that's how you get this number. And you can actually calculate the mean pretty easily, right? Just multiply each and add together, right? And the variance will be just every number minus the mean, take a square times probability, so on and so forth. You get this number, okay? And this example try to illustrate the idea that you can calculate in alternative way. Instead of x, you calculate x squared, lead to 0, 1, and 4. So that get you the answer. Okay. So once you calculate that, you can calculate the expected x squared with the same thing. Okay. This multiplied by this plus this multiplied by this and this multiplied by this. Okay. You get 3/2. Okay. And the variance of x will be 3/2 minus square of the mean is 1/2. Okay. So this is just to try to show you this calculation is easier, especially when you have large number of outcome, and also easier when you actually do Excel, right? Because there's x, there's a p, then you just square of that and then multiply, then things become easier. Of course, there are many ways you can do it. I mean, there's no which sometimes we will think this is easier, and especially when you try to read the proof I don't talk about in the class, that this expression will be something makes things much simpler to calculate. Okay, and if you really want to have more than one variable x and y, we implicitly use it, and we have to define covariance. This covariance idea exactly the same idea if you repeat the experiment x and y, right, many times, and that would be what we observe. Okay, so in this slide we don't talk about formal talk about more than one random variable. Okay, but you can imagine that, look at the random experiment. Okay, an outcome may not be easily summarized by one random variable, can be summarized by two random variables, right? Suppose look at the stock market, only have say two stocks. Okay, it's not easy. You may sometimes want to say, okay, the two stocks or more than two, then you may want to summarize it as a stock market index, right? Hence an index, right? The way you summarize the stock market. But sometimes you actually can't really do it, right? And in that case, you may end up with you need more than one number to represent the outcome. Okay. In the simplest cases, you can use two numbers, right? Maybe X is stock, Y is the bond, and so on and so forth. Or depends on you have two portfolio and two assets in the portfolio. But of course, you can generalize it to any arbitrary number, right? Can X, Y, Z, A, B, C, D, E, F, G is fine. Okay. I mean, but of course, when you have more than one thing, right? The main thing is how these are correlated, right? How they're related, right? What we learn is how to measure things are related is called covariance or correlation coefficient, right? So the same idea here, if you repeat the experiment, each outcome will have X and Y can be described, and you can do the same idea. You have a scatter plot, you have a covariance, right? And as I mentioned at the before the break, right? The variance of x plus y will be, in that case, will be the sum of the two, but you add a covariance. Okay. And actually, some of you asked in the break, during the break, why you want to add the two variable, right? Suppose x is a tossing a coin, y is a rolling a die. Why you want to add them, right? And of course, in those cases, you don't add them, right? You don't add them when adding them is meaningful, right? For example, x is you have a portfolio or a project. X is the return of from the equity. Y is from the bond. Then x plus y is the total value of the portfolio. Then it makes sense, right? You only add them when it makes sense. It doesn't make sense, you don't need it, right? But later you see a lot of application. We actually do a lot of addition, right? Because it's the simplest operation you can imagine, right? Of course, you can do multiplication as well, right? But in that case, you don't have this kind of simple thing, right? But this telling you that, I mean, this is fine, right? As when they add, right? I mean, you can also imagine that there's sometimes you care about x times y, okay? You care about that, okay? The thing is, you can have that, but sometimes it may not easy to have a nice formula for that, for our purpose. But what kind of thing you can calculate, okay? But just in case of addition, there's a simple formula for that. And in this particular formula, when the independent is sum of the variance, we actually will utilize this many times. Same as this formula, we'll use it a lot of time. So that's why we have to mention it separately. And later you will see why we care about independent, because you're satisfied when we talk about random sample, right? Because each draw is dependent, right? Because when we try to have an observation from the data, right? If the random sample, each draw is dependent, right? X is the value of one observation, Y is other value observation, right? And so that's why this is needed, but later you will see, okay? But I hope that is clear what we're doing, okay? So this is something that, I mean, you will be doing more complicated version when we look at the investment class. But let's see why you want to add them, right, in application. So consider the case where the mean return of x and variance of y coming from 0.1 and 0.05. And you ask how I get those, usually hit from historical data, right? And some of you actually ask me how historical to be historical data we look at, right? How long the period before? There's no hard and fast rule, right? Depending on how much data you have, right? Maybe 3 years, 5 years, 10 years. I mean, or 1 year, depends on what your boss said or what have been done so far. So, I mean, usually you're not very innovative in terms of methodology, right? Basically, your boss tell you to do so, right? Or what has been done in the previously. So you don't need to worry about what to do, because usually some have done it, right? If you in the situation that you are allowed to choose whatever to do, then you are already boss, so you should know how to do, right? So usually when you're not boss, usually you don't have to be innovative, right? But if you really want to innovate, you just look at how other people are doing, so you know what to include, okay? So we take it a given our class, right? We don't tell you why it comes from, but we try to look at the projects, so that will be something you might need to do it. But stock-wise, you have this, okay? The mean and variance, okay? And we have a strong assumption here, they're independent, okay? The reason we do it is only affecting how we calculate variance, okay? And of course, if they're not independent, you have to make some adjustment, as we said just now. And this actually is the main thing about investment, right? Try to make sure that the variance is smallest while maintaining a good balance of return and variance, right? And here we assume that it's going to be equally split between the two, right? And of course, in investment class, they will tell you based on your risk characteristic, then you should decide what's the optimal mix, right? That is one of the main things about investment class. Let's try to see what's given the data, what's the optimal portfolio you are going to manage, right? in this particular case, we look at half and half. That means that the portfolio value will be half of X and half of Y. That is this will become the expected return, 7.5% of your portfolio return, right? And the variance is rather simple. It's just variance of the two. Do look that the main tricky part is you take the 0.5 out, it becomes 0.5 square. Okay, just that is the only thing I want to remind you. It's not that straightforward compared to the expected value case. This is a key thing here. Okay, and that's how you get the result. Okay, and I hope that's clear why you would care about summing variable in this example and why this can be very useful in general. I mean, when you learn about things in the future. Is that clear? I mean, if you actually doing content finance or more, this will be something you would do a lot. Okay, but we are not investment class, so probably we stop here. We talk about other things. Is that okay? Is there any question before we proceed? Any question? Okay. If there's no question, then we will continue. So the rest of the class, I mean, I think we still have 10 to 25 minutes. Okay. So what we are going to go over is to go over things that is commonly used discrete random variable, and things we go over. Actually, most of them have actually every one of them have application. So in the real world, there are many kind of possible way a random variable can look like, but these are commonly used one, and you can easily look at Wikipedia or pick up a textbook. They will give you thousands of different kind of distribution. But the one we give you is you can find a textbook, and also very useful when we try to model. Okay, so basically what we are actually doing is in the regime of what we call the probability modeling. Okay, although we don't talk about this, it's like we will have some random variable looks like different shape. Okay, the one you learn in the high school, the bell curve. Okay, that we'll cover in the next class as a continuous distribution. Now we have a discrete, so the form we use is uniform, Bernoulli, normal, Poisson, or hypergeometric. Okay, so all these will be very useful. Okay, has a lot of applications. So let's get started. Okay, and you will see how they're useful. Okay, and uniform distribution, actually we have been using it almost all the time. Okay, it's just saying that each outcome is equally likely. Okay, and actually when we roll the die, okay, actually we have outcome from 1 to 6, right? Outcome, the support is 1, 2, 3, 4, 5, 6, and each outcome is equally likely. Okay, so in those cases, uniform is the most standard thing we have been doing. Okay, so that is the first thing you have been working on so far. Okay, and if you try to draw px, right? So if x is 5 value, it's just like this, all flat. If 3 is just all flat. Okay, the bar chart is the same thing, same height, and say this height, right? You only have 3. This is 1/3, right? 1/3. If you have maybe 1/3 is not entirely clear. 1/3 is here. Maybe I should use this color. Right, this is 1/3, right? And you have this. This is 1/5. Okay, so this is very simple, right? When you try to describe this, okay. And why we care about this graph? Okay, why we care about this is because of we care about the probability modeling. It's the fact that if you collect data, okay, you don't know what it looks like, okay, and you want to come up with a mathematical model to describe what's going on there, then look at the data. Okay, you collect data. If you look like this, rather flat like this in this way, you can use the uniform one. Okay, And you can do all the calculation, do the prediction, do the calculation that you will see later. But that is how you were trying to use this, okay? So that's why I look at the graph is, you look at the empirical data, if you look like this shape or similar shape, then you can use uniform, okay? And this one is one of the most important thing in our class. It's called Bernoulli distribution, okay? Bernoulli is a guy, okay? That's why the name is called. And you look at the history of probability theory, Bernoulli's family is very important in terms of making progress in probability theory. And probably he and the Fermat and all the people, basically you can call the fathers of probability. Okay, they invent probability. And they look at the problem is the following. They look at a very simple thing. Okay, it's like tossing a coin, right? Tossing a coin, there are two outcomes. You have tail or head. Okay, and we used to look at is a two outcome is equally likely. Okay, and they look at the outcome that is not equally likely. Okay, and they call two outcome instead of head or tail, they call failure or success. Okay, and instead of putting 1/2 to each, we will call the probability of success is P. Okay, and success and failure are mutually exclusive, right? When success cannot be fail, when the failure cannot be successful, so that's 1 minus P. Okay, because adding them up should be 1, right? So, and the two outcomes, success or failure. So same as what we call the tail, we will define it as number of success. So that's why it's 0 or 1. Okay, and because we like success rather than failure, so that's why we count number of success. Okay, of course you can also count number of failure, but the tradition is being we count it as number of success. Okay, and what is P of X, right? So in that case, right, X is either failure or success, right? This is fail. This is success, right? And the P of X is just P and 1 minus P, right? So this is what this statement is, right? You can basically have this one, right? And we have this table. And mathematically, you can write in this compact form, okay? And you may ask why this, we will talk about this 2 slides afterward, okay? And trying to convince you, if you write in this form, it's no different from this form, okay? This looks a little bit ugly, but this is the form that is the form that will be useful, okay? So if your X is equal to 0, okay, in that case, what is P of X, okay? Is P to the power 0, right? 1 minus P to the power 1 minus 0, okay? You learn from the high school, whatever number raised to the power 0 is 1, okay? Except 0, but it's 1, right? So that's why this is 1 minus P, right? And when X equal to 1, P of X is equal to P to the power 1, 1 minus P, 1 minus 1, right? So this is 0, so that's why it's P, okay? So, of course, this is a very strange way to write this, but when I first learned this, I don't understand why they're doing this, but it will be immediately clear when I talk about in the next slide, okay? We talk about binomial distribution, that will become very clear why we want to write this, but this is no different from writing, I write in this form, right? This is no different from this table, okay? This is exactly the same thing, but instead of presenting a table form, we will present a compact form, which will be relevant very soon, okay? And why this is useful? Because this is like tossing a coin, or you can always partition your sample space into 2 parts, success or failure, and this makes calculation easier, okay? The easiest thing you can imagine. Of course, immediately you will ask the question, what happens if you have more than 2 outcome, 3 outcome form? We can do it, okay? There are formula for that, but we don't really want to say, we talk about binomial. If you want 3, will be trinomial distribution, right? And multinomial, so on and so forth. But life, we just focus on things that are easier to handle, okay? Just focus on 2 outcomes. And we don't prove it, okay? That will be in the technical slides. But actually, you will see the expected value is P. The variance is P times 1 minus P, okay? So the first one, expected value is P, okay? Actually, maybe we can prove it because it's rather simple, right? Because expected value is just 0 times 1 minus P plus 1 times P. 0 times anything is 0. So that's 1 plus 1 times P, so that's why it's P, right? So that is very obvious, right? When P is close to 1, right? Then your expectation should be very close to 1, right? When X is 0, it's also 0, right? Exactly the P, okay? And the variance is slightly a little bit tricky, okay? And you can easily prove using the math, right? Because it will be just 0 that will be, how do you get this? It's just 0 minus P, right? Because 0 minus P times n square times 1 minus P, right? And plus 1, the value 1, okay? Minus the mean, which is P, right? And square, okay, times P, okay? And do some simple algebra, you can get this one, okay? And well, don't worry about the simple algebra because I'm not expecting you reproduce that in any exam or assignment, okay? And for your purpose, you can just memorize these 2, will be sufficient. You don't need to derive it, okay? Even when I was a student in actuarial science, okay, these are all the formula when to the exam they given to you, so you don't need to memorize formula, okay? So don't need to worry. But just the interpretation of this guy, variance of X, okay? Try to draw this diagram here. P here, P can be only from 0 to 1, right? And I draw a diagram P times 1 minus P, okay? So let's go back to your high school math here, okay? When P is 0, P times 1 minus P is 0, right? When P is 1, P times 1 minus P is also 0, right? And you know that it is a parabolic curve or a contorted curve, right? Something like this would happen, right? The maximum point, I mean, if you learn calculus or not, but you would know this 1/2 is here, right? The maximum is like this, okay? So you will see the variance is the largest when P is 1/2, right? Smallest is the two side, okay? That's the thing I want to talk about, okay? When P is close to 0, close to 1, what we expect the data you will observe, we will repeat it. If P is close to 0, what you see is most of the outcome are all failure, right? So the data you have is all, the number you have is always a lot of zeros and some very few ones, right? That means the variance is very little because most of them are 0, right? So the variation is very small because the mean is also close to 0, so the variation is very small. Similarly, look at the case where P is close to 1, okay? In that case, a lot of data are 1 with very small number of 0, okay? The mean will be very close to 1, okay? The variation is also very small, okay? But so that explains why when the case, when P close to 0, close to 1, then the variance is very small, right? In particular case, when actually say P is 1, the data you observe is everything is 1. The variance is 0, right? Exactly 0. There's nothing, there's no failure, everything is success, right? When P is exactly 0, every outcome is failure. The variance is 0, right? Because every outcome is 0, mean is 0, variance 0. Okay? So here comes the big thing is when P is 1/2. P is 1/2 what we expect. Half of them are failure, half of them success. Right? And the mean is exactly 1/2. Right? So every outcome is either 0 or 1. right? The mean is 1/2. So the distance is always, every observation you have, the distance is 1/2 from the mean, right? You take a square, you sum it up every time. So that's the maximum variance, okay? So, or in the other words, you would think the following, right? If this is likely to be success or failure, then the most uncertainty appears, right? You don't know which side to go, right? If it's clear it's biased one way or the other, right? The variance is very little. Is that clear what this means? I hope that convinced you why this is it looks like. Of course, you can prove it in math, but I think it's important to look at the meaning of the expression. Is that okay? Is that okay? Any question? If not, then I want to go to, so this is what it looks like, right? And if P is half, then it looks like this, right? And when P is small, then it's more likely to fail the success, then it look like this, right? This higher than this one. Okay, if P is like this, if P is lower like this, if P is high like that. Okay, so that is something looks like, but this is not something usually you do because only one outcome, success or failure, so it doesn't really worry about this part. I'm not going to prove anything because although it's very straightforward, but you should be able to do it. So I want to talk about this. Probably we'll end this, we'll finish this part today. So that's called the famous binomial. If you learn M1 in the high school, you will see it, okay? So this is nothing but you just repeat what we have done, okay? Repeat what we've done n times, okay? And the key point is this is independent, okay? It's independent. So each outcome, each time you do is independent of what we have done, okay? Just you can imagine the casino, every time you do, it just doing the same, you're doing the new thing, okay? You do the blackjack. Once you do, you throw away the deck, you do it, take out the whole deck and do it again, okay? It's independent, okay? Independence is important, okay? And so what possible outcome you can get, right? You can have be just like head, tail, tail, head, right? So you will be many possible outcome, okay? It's complicated. But what we only care is number of success, okay? We don't care about how you become success, okay? It doesn't care about usually success, success, failure, failure, or failure, failure, success, success, right? Suppose n is 4, right? You don't distinguish how you get successful, okay? Say you don't care about whether it's success, failure, okay? As long as the number of success is the same, okay? In that case, okay, what you will get, look, we learned combinatorics, actually what you learned the last class, okay? It's like this. This is almost coming from before, okay? Remember the one we have is Px times 1 minus P, 1 minus X, right? And this is very similar to here, okay? So first, let me explain why we have this first, okay? Why this first, okay? This term exactly follow from the idea we learned from principle of counting, okay? So suppose the n's outcome, we want x of them are successful, okay? That means we want to success for x time, and then rest of failure, okay? What is the probability of that, okay? Probability of that will be just because we want success, right? X of them, and then you will be failure. That will be n minus x of them, right? So remember the independent, right? So the intersection, right? When the independent is just multiply. Remember last class, if probability A given B, the independent, same as probability A, okay? So probability of first success is P, right? Then probably the second success also P, right? The independent, so you can multiply. The X time of P, so that's P to the power X. The rest is 1 minus P. So that's why 1 minus P to the N minus X. Is that clear why this is the case? First, is this notation is you have X time of success and the rest of failure. And because the independent, right? So you can look at things one by one, right? Because that's what the independent means, right? Is you want first success and the second success and second first success and so on and so forth. We can look at them independently, right? And each success, each one is success as probably P and 1 minus P. So that's why you multiply that. Is that clear why this is the case? Is that okay? Okay. So you want to ask why we need to multiply this guy and NCX, right? The reason is being that we just focus on the particular case where you got success and a failure, right? But it can be, for this, you can do swapping. Okay? How many times you can swap is called NCX. Exactly the same what we do, how many number of ball there, right? So what you do is you have ball number 1 means first success. Okay, suppose you have the, basically what you do is you have ball 1, ball 2 up to ball N, right? And each ball means whether success at that particular trial, right? How many ways you can take out the ball? Because there will be X success, right? So it's NCX. Okay, that's exactly what we do in the last part of our topic 2, right? Just the idea of this is exactly, let me go back to the slide if you, sorry, I just go back to here. This is exactly what we learned from the probability theory. If you don't fully remember, it's exactly coming from this particular slide. We toast the coin 4 times. How many times we get 2 successes? 4C2. Okay, this is exactly the same idea here. Okay, is that okay? The reason, let me repeat once more, I think this is important to understand what's going on here, is you have this first success and then all failure, right? But you can also have success, failure, right? And then so on and so forth, right? You can just swap these two, right? Okay. How many different ways you can swap? Okay. It's coming from NCX, okay? And you can take it as given. If you don't, you can't follow, but if you really want to follow, basically the idea is you have n different balls, okay? If you draw ball number 1, which means that the first try is success, okay? And because you want X success, okay, basically just asking how many different ways you can draw X number of balls, right? Because if you draw X ball means that actually this X time will go successful, okay? So that is how you do it. If you don't appreciate it right now, that's okay. Because when I learn it, I don't really know it, but I just take it as given. This is the result. Looks right, that's fine. But once you think a little bit deeper and take more time, then you understand. Okay? But if you don't understand, that's fine. I mean, because no one will ask you why did it look like this, okay? You just do it, okay? So don't worry about it. Now, you will easily see why the mean is like this, why the variance is like this. Okay. So this is coming from idea the following. Okay. So X is coming from the fact that you have X1 plus X2 up to Xn. Okay. And you can easily see that each one is exactly the binomial trial, right? Because basically binomial, you can define in this way, just like the X is just sum of n binomial trial, okay? So you remember from the last slide, each has mean of P, okay? So the expectation of The sum is sum of the expectation. That's what you mean, right? We learned before the break, we learned the formula, expected x plus y is expected x plus expected y, right? In terms of English, is sum of the expectation or sum is sum of the expectation, right? So expectation of this sum is sum of this expectation, right? Expectation of each guy is P. Okay, so that's why n times P, the n of them. Okay, I mean, of course, you don't need to, if you don't follow the math, it doesn't really matter because stick is given. Okay, but the idea is very simple, right? Make it simply look at the case of toasting a coin, which is fair coin. Okay, suppose you toast a coin, say 6 times. Okay, you call number of head is success. Okay, what is the number of head you can get out of 6 coin toasting? Okay, it's 3, right? 6 times half, right? 3 times is head, 3 times is tail, right? Suppose you toast a coin 10 times. What are you expecting? Half of them is head, half of them is tail. How you get it? 10 times 1/2. Okay, n times P. Okay. So the variance, okay, I think that's the most tricky part is this variance, okay, is NP times 1 minus P. You may immediately ask why is not n squared, okay? Why is not n squared? The reason is being that it's not, or we are not calculating the multiplying one outcome by n times, it's adding them n times. So actually what we're using is variance x plus y, because they're independent, which is equal to variance x plus variance y. Okay, that's what the formula behind. So each guy have variance P times 1 minus P, the n of them. Okay, so that's why it is. Okay, so we're using when they're independent, that is variance, the sum is sum of the variance when they're independent. Okay, so probably I should end here. Of course, if you don't fully follow the math, doesn't really matter. I'll just give you the intuition. What you need is just the formula there. So I'll just give you the idea if you want to read the proof, but otherwise we're okay. So I will see you on Thursday. Thank you.